Okay, hello all. Today topic of discussion is L2 forwarding and Vxlan with control packet flow using P4-OVS. Myself, Sandeep Nagapattinam, working for Intel in EPG Group as a cloud software engineer, and I have my colleague Nupur Uttarwar, who is also a cloud software engineer working for EPG Group at Intel. First, let us see what is a P4-OVS and what is its architecture. So P4-OVS is built on top of legacy OVS, where we have introduced P4 intelligence to OVS, and also we have introduced multiple applications like P4 runtime applications and open config applications. So to enable our topic of discussion today, we have introduced three more modules inside P4-OVS, where the three modules that are introduced are Switch Link, Switch SAI, and Switch API layer, where Switch SAI is built on top of open sourced SAI layer, and it will be talking to the multiple applications. In one of the application here is Switch Link, and another one is FDB in OF Proto layer. Switch SAI layer receives messages from Switch Link layer, which is talking to the control plane of OVS, where it receives a netlink messages for the underlay connectivity, and then it will be translated into a SAI attributes and then passed to SAI layer, where it will go ahead and program our backend. Similarly, another application which talks to Switch SAI is our FDB in OVS, where it programs the overlay networks FDB entries. Also, the P4-OVS is a TDI compliant and a generic solution to offload P4 data plane on both software and hardware platforms. Currently, we are going to target, or we are going to show a demo for a DPDK target, but this also works fine for Intel ES2000 cards. So to enable current use case, we have come up with a Linux networking.p4 program, where this program clearly differentiates between host to network coming packets and the network to host packets. Also, this P4 program has an intelligence to differentiate between your control packets and data packets. Since our main target is for L2 forwarding, the control plane differentiation it does is for your R packets. So based on the rules that were programmed on a DPDK target, the packets will be forwarded to either your overlay control plane, which is your OVS, or your underlay control plane, which is our kernel. Also, this P4 file, based on the rules that are programmed by user or by learning of FDBs in kernel or OVS, it will also go ahead and program few more tables, which would be used when a data packet hits your target. So here are the tables that will be populated based on the events. So for example, when an OVS creates a Vxlan port on the kernel, it goes ahead and programs Vxlan encap on table and IPv4 table with respect to actions Vxlan encap and decap outer IPv4 action. Also, when there is a neighbor entity learn that has happened on your kernel side, it goes ahead and programs these 7 tables with their respective actions. And this will work for underlay connectivity. And similarly, when there is an overlay connectivity, FDB entry that is being learned on OVS, it will be programmed to our backend target. And these are the 3 tables which will be programmed. And these are the actions for these 3 tables which will be programmed. If you look at this table clearly, the overlay connectivity, we are trying to program same table twice, but with the 2 different actions. This will clearly differentiate if the action is for your overlay connectivity, or if the action is set on it will try to tell that connectivity is for your underlay. So here is the topology that we are going to target today. And this topology is on top of a host where we are running P4-OVS. We can also see there are 2 applications running along with P4-OVS, which is your P4 runtime client and open config client, which would be using to program our pipeline and also configure ports on the backend. Here, since the target is DPDK, we are having vhost user ports, and on top of which we'll be spawning our VMs. So these VMs will act as our overlay network. Along with the vhost user ports on our target, we also have tab ports, which acts as a control port for these vhost user ports and also for our physical ports. In this topology, tab 0 is a port which acts as a control port for our vhost user ports. That means tab 0 acts as a control port for our overlay network. And tab 1 and tab 2 are the control ports for our port 0 and port 1, which means it is a control port for our underlay network. Also, this tab 1 and tab 2 will act as a TEP termination ports. Along with the creation of these control ports, we go ahead and create port represents to these particular VMs, which are VLAN 1 NetDev, VLAN 2 NetDev, and so on. So it is a one-to-one mapping. Any VLAN 1 NetDev corresponds to your VM1. And how this mapping is made based on the control lane rules that we program on our DPDK target. For example, any packet coming from VM1, we go ahead and mark the packet coming on VM1, which comes on vhost user port 0, should be tagged with the VLAN 1, and it need to be sent to your tab 0 port. Since these VLAN netdevs are sub-interfaces of tab 0 ports, the packet, once it reaches your tab 0, it will directly go to your VLAN netdev. These VLAN netdevs, along with the Vxlan port that we have configured for OVS, will be part of a single bridge. That means any packet coming to your VLAN netdevs, any broadcast packet will be reforwarded to all other ports. And all other ports, it will, once it reaches there, it will either go to your overlay network VMs, or it will come to your Open vSwitch kernel module, and then it gets encapped and sent out of your tab port. Here we go ahead and see a quick animation on how broadcast packet that is sent from VM1 will reach to your overlay network on your peer, and then once your peer receives or replies back with an unicast ARP reply, and how it reaches back to your VM1. So this red line, which is coming from your VM1, is an ARP broadcast packet. Once it reaches your DPDK target, there, based on the control rule programming that we have made, the packet will be encapped with a VLAN. In this specific case, it is VLAN 1, and it will be sent to your control port, which is tab 0. From tab 0, this packet will be going to its subinterface, which is VLAN 1, since the packet had VLAN as an tag. Now this packet goes to your bridge, OVS bridge. Now the packet is handed to your OVS, where an FDB learning will be happening. The FDB learning says VM1 MAC has been learned on VLAN 1. At this very moment, our switch link, our switch side code will be triggered with OVS entry, and we go ahead and program a table inside target saying that L2 forward TX table with VM1 MAC as your match key, and action is L2 forward, which is forwarding to this packet to your VM1 port. Since this is a broadcast packet, the moment the packet reaches your bridge, it will be forwarded to all the VMs, all the VLAN ports, and also onto your Vxlan port. Here, the moment the Vxlan port reaches your kernel, the packet will be encapped and try to send to your TAP1 port. If the TAP1 connectivity is not there, the ARP request will be sent for your TAP1 to make sure your underlay connectivity is enabled. Once the underlay connectivity is enabled, we go ahead and program few more tables in the backend, which are L2 forward RX table, IPv4 table, next stop table, and IPv4 table. IPv4, sorry, it's a typo, it's a next stop table. It will go ahead and program this table in your target. Once this programming is done, your ARP broadcast packet will be encapped and sent on to your TAP1 to its corresponding physical port. At this very moment, the packet goes out of your physical port. Once this packet reaches your peer host 2's overlay network, where it replies back with an unicast reply, the unicast reply comes back to our physical port. Since it is a control packet, the packet goes back to your TAP port. And since it also acts as a TAP termination port, here the outer packet will be stripped off and the packet will be sent to your kernel again. When I say kernel here, it's an Open vSwitch kernel module. From Open switch kernel module, it will be sent to your OVS. And at this very moment, a MAC or your FDB learning will be happening on OVS again, where it says your host 2's overlay MAC, which is host 2 VM1's MAC, is learned on Vxlan port. And at this very moment, our switch API will be further triggered again. And then we go ahead and program another table in your backend, which says L2 forward TX table with match key as host 2 VM1 MAC, and the action is set tunnel. If you see, the overlay network action is L2 forward, but for the underlay network, the action is set tunnel. Now this packet from OVS need to go back to our VM1. Now the destination MAC on this packet is our VM1's MAC. Since VM1 is already learned, it doesn't need to send to any other port. The packet will be directly forwarded to your VLAN 1 netdev. From there, the packet will come to tab 0 by adding a tag. Now, based on our control plane rules, this packet will come to our DPDK target, and it will remove the tag, and the packet will be sent back to your VM1. At this point, we can see an ARP learn has successfully happened on VM1. Going forward, any data packet from VM1 of this host to any overlay network of where it has learned, for which it has learned ARP, the packet doesn't need to take all this path. It will come to your DPDK pipeline, where it gets where it hits multiple tables, and the packet will be encapped and then sent out of your physical port. So we have seen a theoretical explanation of this. My colleague Nupur will be showing a quick demo of this one. Nupur, over to you.
Sure. Thank you, Sandeep, for explaining how kernel control plane acceleration works via P4. Let me go ahead and share my screen. So today I'll be demonstrating the Vxlan overlay scenario, which Sandeep just explained. For better visualization, I have color-coded and renamed the terminals. So on the top left, I have P4-OVS running on host 1. Bottom left is the configuration window where we'll be creating the topology for host 1. And on top right, we have VM1 on host 1. And the bottom right is for the host 2. So I have already started the P4 application, P4-OVS application on host 1. As you can see, the OVS database server process and OVS vSwitchD process is already running. Before we go ahead and create the link ports, we need to expose these physical ports to the user space interface using any DPDK compatible driver. So we are using VFIO PCI here to expose these 1800 and 1801 device to the user space interface. Let's take a quick look at the topology. So first step will be, we'll be creating these physical link ports and the corresponding tap ports. These two are the tap termination port, and this is the control port for vhost user ports. Second step is setting the P4 pipeline and creating the Vxlan port. And the third step will be to configure these VLAN port representers and then configure the rules to handle the control packets. So I have the scripts for that. Let's see what the script does. So we are using OpenConfig GNMI CLI to create our ports. So the first set of rules, first set of CLIs are to create the physical ports. For physical port, the device type will be physical device, and the corresponding tap termination port for port 0 will be tap1. And we need to specify the PCI BDF. And the packet direction network means that this port is capable to receive traffic from outside network. And for physical port, the port type will be link. So I have two CLIs for port 0 and port 1. The next set of CLIs are to create the tap ports. For tap ports, the port type will be tap, and the device is a virtual device, and you can name your ports as tap 0 and tap 3. Then the next set of CLIs are just to assign the IP address to the tap 1 interface and bring them up. So let me go ahead and execute this script. As you can see, the ports are created, and we see, since we are listening to the notifications, as soon as we add the IP address, switch side route is created for tap1 interface. The next step is to set the P4 pipeline. So I have the Linux networking binary executable already created using OVS Pipeline Builder. It's a utility which gets installed as part of the OVS installation. And we are using the P4C compiler with PNA architecture to generate all the artifacts required to generate this binary executable. Let me go ahead and set the pipeline. Okay. Once we are done setting the pipeline, we'll go ahead and configure the rules and VLAN port representers. So let me open the script for configuring the rules. Sorry about that. So here we are creating the VLAN 1 and VLAN 2 net devs on top of tab 0 and adding them to the OVS bridge. Then for configuring rules, we are using OVS P4 Cuttle utility, which expects us to provide the target DP index for each port when we are programming the rules corresponding to that port. We can target DP index is nothing but a unique identifier for each port. We can query this information using a GNMI CLI get command. I'll show how to do that in a bit. Let's try to understand what the rules are and how they are getting programmed. So basically, the first set of rules are to handle the control packets coming from the overlay network. So first set of rules says that for VM1, if any control packet is coming from VM1, pipeline should add a VLAN tag 1 and send it to tab 0. So we go ahead and program the handle TX control packet table with action as push VLAN forward, where the VLAN tag 1 is added. Same thing on the other hand, if any packet is coming from tab port 0 with VLAN tag 1, pipeline should pop that tag and send it to VM1. So we go ahead and program the handle TX control VLAN packet table, where the match key is nothing but input port, which is tab 0 and VLAN tag 1. And the action programmed is pop VLAN forward and send it to the VM. These set of rules are for VM2. They are similar rules. Then nextly, we program the rules for handling the control packet coming from the underlay network, which are nothing but your physical port. So any control packet coming from the physical port should be sent to its corresponding tap termination port, which is tab 1 in this case. So we go ahead and program the handle RX control packet table with action as set control destination. And similarly, on the other side, if it's a TX packet, if any packet is coming coming from control port 0, it should be sent to the physical port 0. And here we program the handle TX control packet table with action as set control destination. And these third and fourth CLIs for the physical port 1. So let me go ahead and, so as I mentioned before, we need to query the target DP index for when we are programming the rules. So let me go ahead and do that. I'm just querying the target DP index for tab 0 port, which is nothing but 6 here. And nextly, we can configure the rules. Once the rules are configured, we go ahead and configure the Vxlan port here. So the local IP is nothing but the tab 1's IP 40.1.1.1, and the remote IP is the host 2 tab termination IP, which is 40.1.1.2, and the destination port used here is 4789. As part of programming the configuring the Vxlan port, we go ahead and program two tables, Vxlan encap mod table and IPv4 tunnel term table. As you can see that in the top window, here we go ahead and program this Vxlan encap mod table with action as Vxlan encap, which is used for encapsulating the packet. And the second table which we program is IPv4 tunnel term table with action as decap outer IPv4, which is used for decapsulating any packet. Okay, at this point, we are done with configuring the host 1 topology. And on host 2, we are leveraging the Vxlan kernel stack, and we have created a Vxlan kernel port, Vxlan 0, on top of the physical interface ENS7850. Let's see what the configuration looks like here. The IP address for the tab port here is 40.1.1.2, which is nothing but the IP address of this physical port. And the VNI ID for this Vxlan port is 0, and the destination port is 4789. And the IP address for Vxlan 0 port is 9903. So let's quickly check if this port is up. And it hasn't lost its IP. Okay, let me quickly try to add that. Okay, and bring the port up. Okay. So before we go ahead and actually run our scenario, let's see if the VM1 has any intelligence to reach the Vxlan port. So as we can see, there is no ARP entry available here. And so before I start my ping packet, let me change this window to run a TCP dump on tab 1 interface. So we are running a TCP dump on tab 1 interface, which is nothing but a tab termination port on host 1. And let me start a TCP dump on tab 0 interface as well. Okay, let's start ping from VM1 to Vxlan 0 port on host 2. Okay, so let's see what's going on here. As you can see, as soon as these ARP entry become reachable, we see that the ping is working. So let's try and analyze the packet, the TCP dump packets, and see what's going on. For better visualization, I've highlighted the fields from host 1 and host 2. So all the fields which you see as part of TCP dump, the blue colored fields are for host 1 and the magenta colored fields are for host 2. So as soon as we initiate the ping, VM1 will initiate a broadcast ARP request, which is seen on tab 0 interface, as you can see that here. Since this packet is coming from VM1, it will have a VLAN tag 1. Now this packet will reach the OVS bridge, from where it will be broadcasted to all the ports along with the Vxlan sys port. So you can see that this request is visible here. If this port has all the information it needs to encapsulate the packet, it will go ahead and try to encapsulate the packet. So we can see that it has encapsulated the packet. This is nothing but the outer header. And 12B5 is our destination, Vxlan destination port. This is a Vxlan header. And this is the original inner packet broadcast ARP request originated from VM1. Once this broadcast packet, encap broadcast packet reaches host 2, it will respond with a unicast ARP reply. Since all these are control packets, because of the rules we have configured, if a packet is visible on tab termination port, it will be sent out via physical port and reach the host 2. And similarly, any ARP reply which is coming from host 2 will reach physical port first, and then it will be visible on the tab port. So we just sent out the broadcast ARP request asking the MAC address for 99003. We have received the unicast ARP response from host 2, and it's again an encapsulated packet. As you can see, we have received the ARP reply. Once we have this ARP reply based on the rule program, we will go ahead and decap the packet, and it will reach your VXLAN kernel port. Once the packet has reached the VXLAN sys port, it is under OVS control, where we already have a FTP entry programmed for VM1's MAC address corresponding to VLAN1 netdev. So because of this FTP entry, we will see that this packet is reaching tab 0 interface. This is the packet. And because of the rules we configured, if the packet has a VM1 MAC address with VLAN tag 1, the pipeline will remove that tag and send it to your VM1. That's how the connection is established between your overlay ports. And let's see if this intelligence is visible now on VM1. Yeah, as you can see, the ARP entry is visible here. And similarly on the host too, if I do IP neighbor show, the entry should be visible for both your underlay port as well as the overlay port. Once this intelligence is programmed in our pipeline, all the further data packets will hit the P4 tables as explained before. So let's quickly take a look of what Sandeep just explained. So once this intelligence is programmed, all the further data packets, we will hit L2 forward TX table, IPv4 table, next hop table, and Vxlan and gap mod table. And similarly on the RX side, we will hit IPv4 tunnel term table and L2 forward RX with tunnel table. We can actually see this information using a DPDK debug CLI. Let me go ahead and change the window to DPDK debug CLI. So we are leveraging a DPDK debug CLI available to see the stats and what is programmed in the table. So as you can see here, the number of packets and number of bytes are increasing, and we can also see which tables are being hit and what action is being hit for a particular table. As explained earlier, for encapsulation purposes, we'll use Vxlan and gap mod table, where Vxlan and gap action is hit for all the 163 packets which were sent out. And on the RX side, we should be able to see IPv4 tunnel term table with action as decap outer IPv4 for all the packets. And similarly, as for underlay connectivity, once we learn the neighbor entry for underlay ports, we go ahead and program the IPv4 neighbor table, neighbor mod table, and next hop table. And similarly, you can query all the other tables and see all the other tables and actions associated with it, which are being hit. We can also go ahead and see what exactly is the content of the table using following commands. So let's take a look at L2 forward TX table and neighbor mod table, what content is available here. Okay, let me just open the files which were created as part of the table content. So we can see in L2 forward TX table, we currently have 3 entries. This is the MAC address of your VM1, where the action programmed is L2 forward, and the action is sent to port 0, which is nothing but your VM1. This is the MAC address of your underlay port, where the action underlay port, and where the action is again L2 forward and sent to physical port. And this is the MAC address of your VXLAN 0 port on host 2. As you can see that here, and the action is set tunnel, since this particular port needs to be reached via your tunnel port. Yeah, this way you can actually see what the stats are and what the contents and which tables are being hit. This concludes the demo for kernel control plane acceleration via P4, and all this code will be available soon in our IPDK repository. And the P4 compiler which we were using to compile our P4 program is available on this GitHub repository, and the standard SCI interface which we are using in our code can be referenced via Open Compute Project SCI GitHub repository. Thank you.